Thermodynamics. So thermodynamics, again, is a different way of looking at the same reactions. We've already taken a look at reactions in terms of balancing equations. How many reactants do I need to react with one another? How many products will I make? Which enabled us to use stoichiometry so we could predict what our expected yield was, and we could evaluate not only how many reactants we would have to put in, but also how good our reaction was based on its percent yield. The next way that we're looking at it is by thermodynamics. So thermodynamics examines reactions by how much energy it costs or is created in the reaction. And it also recognizes that most reactions are multi-step. So think about the way that you even put on your shoes in the morning. You put your socks on, then you put your shoes on. You may have to lace up your shoes. It's not like you suddenly go into your sock shoe right away and you're ready to go out the door. So thermodynamics looks at that. So a bit of vocabulary. Delta H, this delta, remember, is change in, which means final minus initial, and it's the change in enthalpy. Enthalpy is the energy of a substance. So mostly it's the potential energy. It's the potential energy that's found in the bonds, covalent, ionic, metallic, whatever. And it's the potential energy contained in the intermolecular forces. So if the energy contained in the products, what I'm making, is less than the reactants, then my delta H value will be negative. All that excess energy is given off to the environment, and we call this an exothermic reaction. So remember that we still have to obey the laws of thermodynamics, which states that energy is neither created nor destroyed, it just changes form. So if the potential energy that's in my products is less than the potential energy in my reactants, then that excess energy will probably be given off in the form of heat or light or sound or things like that. In our case, heat. So here's a way of being able to look at this. This is called a reaction diagram. And the reaction diagram is looking at potential energy or enthalpy. Either of those terms can be interchangeable over time. And the way that we always look at a reaction is that we always go reactants first, and then it progresses, and as my reaction goes, I create my product. So reactants are always at the beginning, products are always at the end. So in this diagram, I have the potential energy of all of my reactants at some value, and the potential energy of my products. And in this case, the potential energy of my products is less than, it's lower than my reactants, and so this delta H, the difference between the two of them, will be my net change in enthalpy. In this case, this is an exothermic reaction. If it was the reverse, like this, where my reactants have less energy than my products, my delta H value would be positive. This just means that I would have to input energy in order for the reaction to proceed. So a good example is boiling water. Water won't boil unless I put energy into it, so that state change, overcoming those intermolecular forces of attraction, requires an input of energy in order to do that. So again, total energy does not change. This hump right here between the reactants and this top part is called the activation energy. And some books say AE, most textbooks say E sub A. So the activation energy is an energy barrier that has to be overcome in order for the reaction to proceed. So an easy way to think about this as an analogy is a speed bump at the top of the hill. So this is the top of the hill. Imagine that I have a ball that I want to roll down the hill. I have to first get it over this hump, and that takes a certain amount of energy. And so I have to input that energy into the system, and this will be the highest potential energy. So the barrier has to be there. If it wasn't, then the reactants would always become products and you wouldn't actually see any reactants. So there's no truly spontaneous reaction. People talk about spontaneous combustion. Activation energy is that barrier there. So spontaneous combustion just means that the activation energy there was fairly low, that it could be overcome under those conditions. But in reality, every reaction has some sort of activation energy. So I have a handshake analogy, and the handshake analogy is this. Pretend that everybody holds their hands, they stand up, and they hold their hands at their side like this, and everybody's walking around blindfolded. Those are the reactants. And the products are if people just happen to match up and be able to shake their hands. That's a product. Now, you're bumping around with your eyes closed. And so half the time, most of the time, if you bump into something, you might bump into a wall, or you might bump into a person, but the back of the person, or you might bump into them in a way in which your hands are over here and not making connection. So it takes a certain number of collisions in order for there to be a successful collision. And we could say that on average, in this system, it takes about 14 collisions in order for somebody to actually meet up in the proper orientation in order to have a handshake. That's the activation energy, right? So when we're talking about reactions to occur, they have to occur in the same way. They have to occur in the proper orientation to one another, and they have to occur with enough energy. So you can talk about the number of collisions that would be required in order for a successful collision to occur. And another example is the Z effective of a metal and a nonmetal creating an ionic bond. Right, so if I have sodium and chlorine, so sodium and chlorine, as you'll remember, they're on opposite ends. They have a similar Z effective, but chlorine is definitely much stronger than sodium. And so sodium's ability to give up its electron and chlorine's ability to grab an electron, the difference in Z effective is fairly high. That transfer will occur very easily. So if sodium and chlorine are in close proximity to one another, it doesn't take much additional activation energy in order for the reaction to create sodium chloride. On the other hand, aluminum and phosphorus are very evenly matched. Right? Phosphorus is not that strong, aluminum is not that weak. Phosphorus is the main component in match heads, and I can safely store matches in aluminum foil without worry that they're going to create aluminum phosphide. And that's because the Z effective difference between the two of them isn't very high. It takes a certain amount of energy in order to get them to start to react. So that analogy may be a little tough, but you have to understand that what's happening is that everything when we're talking about a reaction, everything from how easily my electron transfers, how easily the molecules have to be aligned with one another, all of that goes into a determination of the activation energy. So here's the activation energy. I can look at reactions as a forward reaction or a reverse reaction. So a forward reaction is what we're always used to. I go from my reactants to my products. I have water, I boil it, I have water and I freeze it and I create the product of ice. That reaction is also reversible. I can take my ice and not go backwards in time, but I can take my ice and melt it, and that would require a certain amount of energy put into it. So if the activation energy of the reverse reaction, that's this green one right here, is a lot greater than the activation energy of my forward reaction, then it means that under those conditions, it's really easy for the forward reaction to occur, but not for the reverse reaction. And so this is a type of reaction that would be more likely to go to completion. Catalysts. So catalysts don't change the delta H. What they do is they lower the activation energy. So back to the handshake analogy. If it takes 14 handshakes in order for you to get a successful handshake, 14 collisions in order to get a successful handshake, the catalyst could be somebody who actually has their eyes open and is able to grab a shoulder of each person and then turn them so that they're facing toward each other. With the catalyst there, it doesn't take as many collisions in order for there to be a successful handshake. And once that person is done turning you in the right direction, they're free to let go and move on. So there are two aspects of catalysts that are very important. One, they're never used up. So the person is, once they finish their reaction, they can go on to the other reaction. They don't get stuck to anything. And the second one is that they lower the activation energy of the reaction. So again, endothermic reactions characterized by higher products than reactants, and so it's basically like an uphill reaction. They're less likely. So if I want to look at it from a Boltzmann distribution curve perspective, because we know that I love that. So this is looking at two different things. Here's my activation energy. My activation energy with my catalyst will be lower, so more molecules will be able to undergo the reaction. This would be the activation energy of my forward reaction. If my reverse reaction was endothermic, my activation energy would be over here, and you can see that fewer molecules in this situation are able to undergo the reverse reaction, the endothermic reaction. If the difference is very high right there, then you could see that this reaction would pretty much go to completion because there are very few molecules that would be able to undergo the reaction. The pink curve shows what happens when I increase the temperature. So increase in temperature actually usually increases the number of molecules that can go through the reaction. I'm shifting the curve to the right, and so even though the activation energy doesn't change, there are more molecules under the curve, the area under the curve is greater, that can undergo the reaction. And this has to do with the fact that I'm not changing the activation energy, it's just an increase in temperature means that the molecules are moving faster, so I'm just doing more collisions in a certain amount of time. So I'm still requiring those 14 collisions. As the temperature increases, the velocity of the particles increase. So again, I'm just having more collisions. So you may ask, how can endothermic reactions occur at all? Well, I just have to increase the temperature most of the time. Right? Another way that endothermic reactions, and to understand this, is that there is another factor that enables reactions to occur, and that factor is called entropy. So entropy is a term that's often used, and people say, well, it's disorder. I find the easiest way to think about entropy is just the number of places something could be 10 minutes from now. The more possible places they could be 10 minutes from now, the more entropy that thing has. So think about it. At a low temperature, I'm usually in a solid state. In a solid state, my molecules are pretty much locked in place. So if I'm right at the edge and I'm in a solid, 10 minutes from now, I'm going to be in the same position. You're not going to see me moving. Maybe I'll vibrate back and forth a little bit, but really not that much. As a liquid, however, I'm moving around. I'm still got intermolecular forces of attraction. I'm still constrained by the volume of my container, but I can still move around. And so 10 minutes from now, if I was at this position, I have more possibilities to be than I was as a solid. I have greater entropy. As I heat up that liquid and the particles move faster through the liquid, again, 10 minutes from now, there are more possible places I could be. And then finally, as a gas, where I'm not even constrained by the volume of this glass, but I take the volume of wherever I am, and I'm moving around at very high velocity, lots of collisions, I have the highest degree of entropy. And as I increase the temperature and increase my velocity, again, I increase my entropy because there are more possible places I could be 10 minutes from now. So there's a very temperature-dependent aspect to this entropy, because it is based on movement. And so I'm increasing kinetic energy, and I'm also overcoming intermolecular forces of attraction. So you can have an endothermic reaction like the melting of ice if your temperature is high enough. So I can cause endothermic reactions to occur oftentimes if I have an increase in entropy and my temperature is high enough. So I have those two competing values. So in order to put that all into one equation, we have this magical equation called Gibbs free energy. So delta G is equal to delta H minus T delta S. So delta G is that measure of spontaneity, that Gibbs free energy that we call. And H, as you remember, is the enthalpy. And you can measure that as far as the potential energy found in the bonds and the intermolecular forces of attraction. And somebody has gone through and tabulated those results. And times T delta S. So temperature is T and delta S is entropy, and T can be in degrees Celsius. It doesn't have to be in Kelvin. And it's a subtractive factor. So entropy, if I increase my entropy, say that I now am in a state of matter where I can move more freely, or I'm at a higher temperature where I can move around more rapidly, that delta S is a positive value. If I move in the opposite direction, I freeze, right? I go from a liquid to a solid, or I decrease my temperature, my delta S will be negative. For enthalpy, remember that if I have a positive value, that means I have an endothermic reaction. And if I have a negative value, I have an exothermic reaction. So if you think about it, if I have a delta H value that is negative, right, exothermic reaction, and I have a delta S value that's positive, then my delta G value will always be negative. And a perfect example of this is a combustion reaction. A combustion reaction, if you remember, goes AB, and it's usually a solid or a liquid, plus O2 yields AO2 gas plus H2O liquid. And this is usually a larger molecule, and these are smaller molecules. And so not only am I increasing the entropy because I am having states of matter that are more free than solid and gas, I'm going from gas to liquid, there also is an exothermic reaction, so my delta H is negative. It's also simpler format, so there's not as much order in my molecules. That's always spontaneous. So delta G value is negative, means that it's a spontaneous reaction. The more negative it is, the more spontaneous it is. What does spontaneous mean in this situation? Spontaneous means that once I start the reaction, once I light that match and I light my stuff on fire, it will continue to burn and I don't have to do anything to it. I can just sort of sit back and enjoy the fuel log burning for 10 hours. The opposite of combustion is photosynthesis. So photosynthesis is taking carbon dioxide and water and putting it together to create something and oxygen, sugar and oxygen. Photosynthesis requires a constant input of light. If I turn off the light, the plant can't photosynthesize. That's why it's called photosynthesis. So that's a non-spontaneous reaction. The moment I stop putting in energy into it, the reaction stops going. So the moment I stop pushing a boulder up a hill, the boulder will stop moving uphill. It will probably roll back down, but that's not the point. So the delta G value, if it's positive, and endothermic reaction and negative entropy, then my delta G value will be positive. And I have to start this again. So what happens if I have an endothermic reaction, so this is positive, but I increase my entropy. So this is positive, but I'm increasing my entropy. An example of that is melting. It requires energy to put into the system, but if the temperature is high enough, the reaction can occur. The opposite of that would be I have something that decreases entropy, my Y value, but it's an endothermic reaction that's freezing, and that can occur if the temperature is low enough. So what this Gibbs free energy tells us, it gives us insight into the conditions that have to apply in order for a reaction to proceed. And it also tells us things like the amount of potential energy that it will take, so the energy cost. So if I'm running a reaction and I realize, wow, the delta H value is so high, it's such an endothermic reaction. In practical terms, that means in my lab or in my chemical factory, I'm going to have to use a lot of energy, burning fossil fuels, putting electricity into it, shining lights on it, whatever, and that has a bottom line cost to it in terms of time and money and resources. So I'm taking a reaction that on paper really is just this elementary reaction and getting some real world insight into it. One, how easy is it for it to occur? Is it temperature dependent? Do I have to put it in a freezer? Do I have to boil it? What do I have to do? And do I have to add energy into it in order to keep the reaction going, either in the form of activation energy or in the form of the fact that it's an endothermic reaction. So one of the reasons why certain products cost so much money to make isn't just because the company is trying to make a profit, but because in the manufacturing of whatever product, it could be that my delta G value is positive and I need a constant input of energy in order for the reaction to occur.